All right, relational databases. So what is a database, right? So in general, basically we have a need to store data for long terms of periods of time, and we like to be able to retrieve that at some point. And we're talking about lots and lots of data that we like to be able to query it somehow, ask it questions, and that it can answer those, presumably about some complex system, right? That ideally the data that we're capturing represents some physical phenomenon, right? Something that can be mapped to some reality, and that the kinds of questions that we might make to the database might answer some questions about that reality, right? And now to what degree of granularity do we capture that data? That's up to us, right? What we might want to capture about maybe a car to a university might be different to what a car might mean to Ford Motor Company or Tesla, right? For us, maybe modeling a car, it would be enough to have maybe the license plate. Maybe that's enough for us to model. For our purposes, that's enough to model a car. Whereas for Tesla, they might need to know every single bolt, right? Every single piece that. So for the model, for them to be able to capture that, I mean, theirs is much more complex. So depending on the domain, different entities, different pieces of data might have different meanings, and what we mean by model is that we want to have a formal representation of some phenomena, right? In other industries, in other engineering fields, they might use a function or an equation, right, that describes some phenomena, some behavior, and they plug in some values into that equation, and then it spits out some values, yes, and then they can make decisions on whether they should put more voltage or not, or put more weight or something, or whatever, right? So based on all these equations that model how their system behaves, right? Us, we are all about symbols, right? All about diagrams and graphs, and we think we can model the world with some tree, with some nodes and graphs. And we can model the entire world. Yes. So us is all about data, right? We're working in the information technology industry, so it's all about the information. We are the keepers of the information. We have to make sure that the information is true, that it's not it's safe, that it's not inadvertently modified by folks that are not supposed to modify it. So to that end, we use databases to do long-term storage. We think of the idea of that certain pieces of data are somewhat familiar, or they're similar to one another, and we try to collect them in all pieces of data that are similar to one another. We try to put them in the same bucket, right? And because they might have the same fields, they might have similar attributes, and all those attributes that make up all those data points that are similar to one another, we call that attributes. We call that a schema, right? The schema that describes or are the attributes of each one of those pieces of data. Those pieces of data, we refer to them as records, right? And those buckets where we put all those pieces of data, we oftentimes refer to them as collections or tables, right? In a relational database, we call them tables and records. And the reason we call them relational databases is that we tend to put information that is like to other information in the same bucket, in the same table, right? And we try to break it up in such a way that that we avoid redundancy, right? That the most naive way to capture a piece of data is maybe an Excel worksheet. We have this really long worksheet that has lots and lots of columns, yes? And we just, for any piece of information that we capture, we just fill out one row, right? And the next piece of information, even though we might not have always all data for all the columns, right? So some columns have some information over here, some columns have some information over there, all in the same spreadsheet, right? That's the most naive way. Typically, what database will try to do is say, oh well, how about all the rows that have the same values for the same columns? Let's split that off, right, and make that a separate worksheet, maybe, yes. And the ones that have most data that for some of the columns, same columns, they make that a different worksheet. Let's split them off, and let's not have just one with lots of empty space, but let's have lots of tables that are specialized for different types of pieces of information. But at some point, we need to be able to reconstruct the data that we have split up into all different buckets, right? Because the personal information might be in that bucket over there, and their address might be in a different bucket, right? And what section they're enrolled is in a different bucket over there, right? And there might be a question that says, well, give me all the students and where are they enrolled? Okay, well, I'll need to go fetch some information from this bucket and from another bucket and some other bucket, right? But not all data points from one collection are related to all the data points in another collection. Yes, only a subset of these are related to over there. So because I am, 50 of you are enrolled in this section, but there's another 40,000 students that are not enrolled in this section. Yes? So certainly we want to, when we ask, we want to make sure that the relationships are correct, right? That we want to only display these students that are enrolled in this section. There's a relationship between the two, right? And that relationship is where relational databases gets its relationship from, right? Is that we split off to normalize the data, but then we have to join it back in to reconstruct the data by following relationships, right? Saying each record knows how is it related to another record, right? It says, hey, I'm the address of that person over there, right? And this section or an enrollment record might say, hey, that student over there, they're enrolled in that section over there, right? So all these pointers, right? All these relationships, we have to follow them to reconstruct the data. So then, hence, relational databases. We're going to be using throughout the semester a theme of using a university that we're going to be talking about students and departments and courses, sections, and enrollments, and that capture certain pieces of information. These are the attributes that describe them. So like student might have a student name, graduation year, major ID. A department might have department name, course title, and whatnot. Section, course, professor, and year offer and enrollment, saying that a particular student is enrolled in a particular section. Okay, so this is a theme that's going to go out through the entire semester. Here's an example of what that data might look like, where you might have in a student table, you might have 4 columns. We have Joe, Amy, Max, right? Their graduation year and their major ID. So this, for instance, that major ID is kind of like a pointer saying, hey, notice that in the department table we have 3 departments, 10, 20, and 30. So that major ID is kind of referring to all these departments over here, right? That's saying, hey, these are all the departments where all these students are enrolled. And here we have also in the course table, we're saying that all these courses are courses in a particular department. So you have your DB systems, compilers, and DB systems and compilers are in the computer science. Calculus and algebra are department 20, so in the math, and acting and elocution is in both of them in the drama department. We have here some enrollments saying that so-and-so student is enrolled in so-and-so section over here. And by the way, that's the grade they got for that particular in that particular enrollment. Typically, if this were the enrollment table had only these two columns that map one student to another, one record to another record, typically we would refer to this as a mapping table, right? It maps one record to another record. Okay. Since this has additional fields here that kind of describe this relationship, so these 2 fields just says that there's a relationship between these 2 records. But this one kind of describes that relationship, right? Well, that's what that student got in that particular section. Maybe you have here maybe some feedback that student gave, for that particular enrollment. I got an A and I love the class. Okay, so additional fields here might describe the relationship. So we call that not a mapping table, we call it an association table. Right? It's associating two records and it's describing that association. Okay. So anyway, so this is some sample data. The university database has students, enrollments, courses, sections, and now how we decided that these were the tables that was the best way of modeling our university. Well, the process of deciding which tables we need, which attributes, what data types, that's what we call designing, right? We are going to design a database, okay? And oftentimes we might be very familiar with the domain, and this design is just natural. Obviously, what other way would you design it? Okay, and it says, yeah, duh. Any other way of doing this? Well, this design is typically based on not only your knowledge of the domain, but also any constraints that might be in the description of the problem statement, right? Typically, this design follows some business requirements, okay? That if you change the requirements, change the data model, right? Typically from the requirements, you say, well, these are the kinds of questions I want to make to the database. Depending on the questions, right, it drives how you're going to store it. If you maybe tweak the question, you might decide, oh, no, this can't be an attribute. This must be a class, right? If nowhere, for instance, is the question of where does the professor have their office hours, or where is their office? Are they tenured, right? What's their contact information? If in the requirements that question never came up, right? Maybe just a username is enough, right? Notice that here we don't have a faculty table, right? So somebody decided that it was enough that Professor Newton or Professor Einstein or Professor Turing was teaching that particular section. And that's all we need, right? Because nowhere did we ever ask, okay, in the problem statement, what is the professor office hours? Are they tenured? Are they whatever, right? What are their benefits, right? So there is no table to answer any of that, right? And that's enough. If instead one of the questions was, I want to be able to list all the professors and their history here, right? Their salary history. Then this would not be enough, right? We would need to have additional tables that would capture records for all our faculty, right? And their history here and whatnot. Okay, so somebody decided that this model was good enough, right? So depending on what the questions you have drives the design. Okay, so this cannot be implemented just because you're knowledgeable of the domain. It's always driven by what kind of queries do you want to make. For one design, depending on the queries, there might be some redundancies in your database. But if you don't have those queries, then it's not redundant. It is okay to have multiple values in many places, right? So the question, is this data redundant? You always say, well, I don't know. What is the problem? Right? If the problem, if for one problem statement there is no redundancy, for a different problem statement there might be a redundancy. Okay, so it depends always the queries, the questions you want to ask the database. So a database system, right? It's a piece of software, right? That's running on some machine, typically a server machine that is listening at a particular port that can receive some network connection and engage in a query, right? That you can send a query over the wire and you can respond over the wire. It's meant to be persistent, meaning that you can shut it off and tomorrow when you turn it back on, the data is still there. So it's for long-term storage. It's meant for large pieces of information, unlike data that might be stored in memory in a program, right? In a piece of software, you only have a very small portion of the data. you only have just a couple megabytes, maybe a gigabyte of data stored in memory, right? But these we're talking about terabytes, right? For long-term storage, huge piece of information. How do you interact with such a huge amounts of information, right? If you you want to make queries and say in memory, you might have maybe hundreds of users instantiated in Java classes in an array, right? And you might want to iterate over them, right? But when you're talking about, well, I want to make a similar query in a database, you might be talking about millions of records, right? So it's a completely different scale of interacting with pieces of information. It's shared, meaning lots of people might be using it simultaneously. People might be writing to the database while other people are reading it. And so how do you deal with all those? It needs to be consistent, needs to be accurate, and usable. So there has to be some interface, such as SQL, that allows you to actually interact with it. So how do we store things? So say we have a student and we want to capture these fields, and we could have just decided that a comma separated values, a CSV file might be enough. That's plenty, or maybe a tabular data is plenty, right? But that's not enough, right? It doesn't allow you to capture any metadata, right? Any constraints, any other things. But indeed the data is indeed obviously eventually just stored in files, right? But the database does a lot of optimization in such a way that it knows that it's structured in a particular way so that it can retrieve it quickly, right? So in addition to storing just the files, it also has auxiliary files that are index files that allow to refer to different blocks in the data file, so that it knows where things are, right? It organizes itself, right? Just like our parents were right when they asked us to organize our rooms because they couldn't find anything, right? It says, how could you find anything in this mess? And they were right? The more organized you are, the faster you can retrieve things. Certainly anybody take algorithms? Right, so depending on the more metadata you can add to your organizing your data, you can get things faster, right? So if you have an unsorted list, well, you just have to do a sequential search, right? A linear search, right? But if you spend some effort into organizing your data, you can improve your performance of retrieving data, right? Going from linear to log n to maybe a constant time, right? So these index files, that's what they try to do, right? They try to organize the data, sort it in such a way that they can retrieve data from the original piece of information, and they will sort the data in such a way that they'll create some tree structures that will allow you to retrieve things quickly. And we'll talk about that when we look at indexing a little later. Multi-user access, so multiple people are simultaneously reading and writing. There's a risk of inconsistency while you're reading. If somebody's changing the data on you while you're reading, right? You could have an inconsistent piece of data there. So yeah, and it could happen, right? It's common that you go to a web page, you're looking to book a plane, and you see that there's 40 seats available. And you select the one that's available, and when you go on, it says, "Oh, sorry, we can't go further because the seat is no longer." But you were showing to me the data that you're reading is only as good as for the amount of time that you're given to make a decision, right? It could be, meaning it's not repeatable. The read is not repeatable. You read it once. Right, and next time you look, it's no longer there. It's invalid. It's already stale. Right? Any piece of information, by the time you read it out of the database, it's already stale. Right? You're already risking the fact that you're working with stale data. Somebody might come in and change it, behind you. So how do you deal with these things? Right? Do you lock? Do you say no? Just lock it down because I'm busy looking at this, making a decision. Twiddling my thumbs before I make a decision. So that's why usually you have these timers. This is good for the next 30 seconds. We can't lock this. We can't guarantee this longer than that. So yeah. So how do you deal with all these inconsistency risks? Concurrency of management of being able to. What do? Do you lock the entire table so that nobody can read it because nobody can write to it because you're busy reading? That'd be way too much, right? Or maybe you lock the record, the single record that you're manipulating, or maybe the only field that you're looking at, right? So what's the granularity by which we can manage the concurrency of these databases? Because we've gone through a lot of effort at doing a multi-threaded environment where you have multiple hundreds and thousands of folks using the system at the same time, and now we kind of want to add these sequential semaphores that force you to sequentially consume the data. You're kind of going against your own architecture, right? So you want to find a balance of how do I maintain the multiple threads running, right, for optimizing the performance while maintaining some level of consistency in my data. And if conflicts happen, which will happen, how do you resolve them, right? We need to have a kind of like a history that keeps track of how do we get into this mess, right? Can we backtrack to a previous state that was a stable state that I know the data was consistent, right? If we do detect inconsistencies, can we roll back any changes so that we can go back to a previous stable state? So transactional updates, allow you to group things that typically would have to be considered atomic, right? That that it's an all or nothing kind of deal, right? If I want to travel to Chicago to visit my daughter, I want to be able to travel there with an airplane. When I get there, I want to have a car to be able to drive to a hotel, and I want a hotel room, right? If any one of those three fails, I'm not going to Chicago, right? So I want to treat those three operations that are individually disparate operations. I want to treat them as if it were a single operation, right? I'm going to Chicago, but any one of those three fails, I want to treat it as one single transaction, right? If any one of those fails, I just want to roll back. So I want to, if I have a flight and I have a room, but I don't have a car, I want to be able to cancel my room and cancel my flight, right? Go back to where I was before I did anything, right? So transactions allow you to do those kinds of things. Group things, multiple operations into an all or nothing to make sure that you can jump back to a safe place if the transaction fails. Authentication, make sure databases need to allow you to make sure that the right folks are actually manipulating the data, that we know who they are, and once we know who they are, we want to make sure that they are the right that they're allowed to do the certain things, right? That yes, I know who you are, but you can't touch that table, right? You can touch these tables, but not that one, right? So we want to be able to authorize also, right? Maintain an authorization and what the privileges are for those users. Also, memory management, right? The database is has to deal with huge amounts of data. But only at small chunks at a time. There's no way that it could actually consider terabytes of data, right? If there's a query that comes back with billions of records, it can only show you so many at a time, right? You can only read so many from disk, right, and show you visually the records that it might give you the semblance of dealing with billions of records, right? But only maybe 100 at a time. So it kind of caches those results in memory, enough to be able to answer questions, right? So it has to deal with all these, especially because going out to the file system is extremely slow, right, compared to accessing records that are already in memory. So it's always doing, having this balance of trying to work with the information that already has in memory without having to go out to the file system. But dealing with the fact that any data that is cached in memory, you're running the risk of working with stale data, right? It's not representative of the actual data that might be in the file, right? Yeah, so it needs to maintain synchronization, make sure that if something changes in the cache, that it also changes back on the files and vice versa, and that you run the risk of inconsistency or outdated. Also, the databases typically deal with data representation at different levels of abstractions. Certainly needs to deal with the raw representation of the data, which is just a file, and perhaps tables that may be broken into multiple files. Right? It needs to be able to reconstruct the understanding of a table at a conceptual level, right? So that you can answer our questions as, select something from a table. What is a table? Oh, it's these files, right? So it needs to do the mapping between the raw file data model to a conceptual model, to a relational data model. The relational data model meaning these files need to map to these tables, to these foreign keys, to these primary keys, and then the conceptual model. A UML class diagram, right? That it's a theoretical graph, right? Diagram that captures very conceptual, very high level data models, right? Yeah. So the physical model is sometimes also referred to as a file system, right? How is it physically written to the file system in zeros and ones? Right. So the impetus for designing these databases or creating databases in the first place was, before databases you had to write some piece of code that physically read the file into memory, right, and then iterated and parsed these files and extracted different features from the file line by line, perhaps answering certain questions. So, for instance, here's an example. Retrieve me all the students that graduated in 1997, right? And it's parsing line by line, reading a particular field, seeing if the year is 1999. If it is, it adds it to a particular result set, right? And once it has iterated over the entire file, it'll have a subset of records that met that criteria, right? And then return some list or collection or array of these students that met that criteria. And once you've done some of these, lots of these queries and iterations and going through these files, you start identifying patterns, right? It says, I always have to iterate over these, right? I always have some kind of predicate that I need to answer. I always have some result set that I need to create, right? So there's almost a for loop involved, right? So you start identifying these patterns and trying to abstract them. You're trying to generalize these patterns. As good software developers, we are lazy software developers. We like to do things manually only once, and then we try to abstract what's the pattern, and then we try to generalize it so that we don't have to do it more than once. So somebody said, well, wouldn't it be nice if we could just write it out? Select the name of a student whose graduation year is equal to 1997. And now I can parse this, right, and feed this as parameters into some for loop, right, that can then iterate through my file and answer that particular predicate, right? So that's what databases are. This conceptual model, this very high level representation that hides all these loops. Underneath, obviously, somebody's iterating over records, right? Somebody's going through a file system and reading all these records and validating this predicate, right? Is comparing this particular field with a particular value, and the ones that are true, that make that predicate true, it returns into the result set or records. Now, there's certainly the relational databases is not the only way to store data. There's plenty other ways that are meant to be used in other aspects. There's certainly object-oriented models where you have Java classes or C# classes that are meant for short-term memory, right? For short-term periods of time where you might have an instance of an object, and then it's gone, right? They come and go very fast, as opposed to records, right? They're here to stay for a long, long time. You have hierarchical models such as XML. You have graph models. So there's plenty other alternative ways of storing data. We're mostly going to be focusing on the relational database, relational model for the first 2-3 weeks of the semester. We'll then explore some object-oriented models when we start looking at JDBC and how to map them into Java. And we'll look at hierarchical models when we talk about XML. Okay. So physical data independence, meaning we want to be able to work at with these databases irrespective of how eventually this is stored in the physical file system, right? Our layer of abstraction allows us to talk about these high-level ways of talking about data representation without having to care about how this is stored in the low-level file system. I'm looking for external schemas. Oftentimes, the way we end up designing the database, right, will be somewhat inconvenient for those who want to consume the data, right? It is the reason we broke up the data in the first place was to avoid inconsistency, to avoid redundancy, right? That we want to store a piece of data only once, right? And that's why we designed it that way, based on the queries that you want to do. But for a day-to-day person that wants to use this data, it might be very inconvenient that the data was stored in this way, right? They would have preferred perhaps a single table that might have had some of the fields from that table, some of the fields from that other table over there, right? In a nice, convenient single place where I can find all my records, right? So most databases provide what it's called an external schema that allows you to create these virtual schemas, right? That can grab fields from different tables and provide not a concrete schema but a virtual schema. For instance, the dean's office, might want information from the student table plus the section table, whereas the registrar's office might want some enrollment and some students, right? They don't want to bother with joining them together. So we can create things such as views, right, that are virtual tables, right, that look just like tables, but they're not physically tables. They're not stored for long-term storage, but they're a convenience for some users of the database, right? And we'll explore some views as well. And the physical schema might have the actual databases, the actual storage of the files that store the data, plus any supporting indexes, right, that allow you to optimize the retrieval of that data, of that physical data.